All right, people, today we are going to learn how to create a very simple neural network model. Okay, now the first thing that we have done in that code I have given you is they do the exploratory data analysis first and then they go for building the model. Okay, so I'll just give you an overview of both of those, what happens and how it happens. EDA, most part you should know what is happening, but I'll tell you once anyways. So you import your drive, first of all. Wait. Okay. And then you get your data from your drive. Okay, all these files that you need to analyze and the CSV file that you need that has all the information about which label are these files from. Okay. And then you import everything. These you already know, these libraries. sklearn also you already know. So these things also you know. SciPy is just for a simple thing. I'll tell you what it is for. And here we have Keras, which is used to create a neural network. Okay. PyTorch is used for the same thing. So if you understand what is happening in Keras, PyTorch also does pretty much the same thing. Okay, so you'll be able to understand that. Okay, so we read our CSV file and okay, it has a column called class. We extract the unique values from it. Okay, which means in labels, we have all the labels that we could have gotten. And then we create a dictionary. Okay, what a dictionary is, for example, a dictionary looks like something 1:09, say, comma, 2:10, say. Okay, suppose that is your dictionary. What it means is these values are the keys. The 1 and 2 are the keys. So if you call, say, dict 1, okay, if you try to print this, what you will get is 09. Okay, because the value of the key 1 is 09. Okay, so that is what a dictionary is. So here what we are doing is, okay, we are going through all the 10 labels. We have 10 labels here. So we are going through them. We have 10 iterations. So first thing we do is if the class is equal to label I, okay, the first label, we are going for the first label. We are finding all the rows in DF in our data frame, which have this first label, okay, label 0, whatever that label is. Okay, suppose that is dog bark. So we are extracting all those rows and we are taking only the first row out of it. Okay, this means starting with 0 and going till 1. And you know that 1 is not included. So all we have is the 0th row, which means the first row that matches the label. Okay, so we are extracting that and we are doing reset index. Okay, this is very important. I will show you why. Okay, so that is done and this is stored in TMP, a temporary variable. Now for the paths, see our paths, because it's the path is from here, it looks like /content/ and then we have the name of the file. Okay, so this curly bracket is used when you want to have a variable there. Okay, not a constant value. This will remain constant. And here inside the curly bracket, you need to have a variable. And format is used to tell which variable it is. Okay, so we say that it is in TMP, the slice file name, and for the 0th index. Okay. Reset index is necessary because because when you reset your index, it will begin from 0, right? So this will have a 0 index now, whatever this row is. Okay, and the name of the file is in a column called slice file name. Okay, if you open the CSV file, you will see that the slice file name has this file's name. So we need to add that file name after content, and that will be our path. And in files, which is a dictionary, for label I as in here we have dog bark, say, and then in dog bark we would have the path to a file that represents a dog bark. Okay, so that is what files will look like. If you print files, okay, see dog bark, and then if you play this particular audio, it would be for a dog bark. Okay, so we have the same thing for all 10 of our labels. Now reset index is important because let me print TMP for you. Okay, see. Since our since our CSV file has a lot of rows, okay, so every row will have a particular index. All right. So here in the 5th row, we have a dog bark. Okay, it's in, no wait, this should be a gunshot. Okay, so it's in the 5th row. The first value for gunshot is in the 5th row. And since we did reset index, its index changed from 4 to 0 again. Okay, and now when we need to call this, we just call this 0th row. Okay, because now its index is changed. If you don't change this index and you try to call 0, it would say that it does not exist because the index is 4 here. And you have no way of knowing which index it is. So you'll have to write extra codes, and it's better that you just reset the index and you say 0. Okay, they extract the first row of it. Okay, so that is why reset index is important here. Now that is clear, we'll move forward. Okay, now since we have one path each, what we are going to do now is we are going to plot it. Okay, we do the figure size, plt.figure. We find subplots because we need to have 10 different figures here for 10 different labels. And we specify the horizontal and vertical space. And enumerate is used to convert any value into numbers. So if there are 10 values here, they will be converted to 0 to 10. Okay, so for I or label I comma label in 10 values, so it will be iterated 10 times. Fn is equal to, this is a variable, and this is equal to files label. Okay, which means fn stores the path of that file, because what we did here was we converted the files. This was a dictionary, right? So the key, any label that is, the key will refer to the path. So this in files, we are referring to the label key, and this will give us the path as the output, and that will be stored in fn. Okay, now we add the subplot. This is 5 rows, 2 columns each. And this is I plus 1 as in specifying the position of that graph. Okay, so if it's, because the I index starts from 0, right? So the first position will go to the 0th graph. That is dog bark here, in this case, I believe. And you give this a title for the label, whatever the label is. And then using Leprosa, you load that path. Okay, since this is the path to that file, you load that file and you find the data and the sample rate. Okay, and then you use wave show, and this will give you the wave, okay, how your audio looks like. So we run this. Okay, there you go. See, 5 rows, 2 columns each, and the heading is the label, whichever it is, and you have all the waves. Okay, how these things look like. Now here, this is just to differentiate between SciPy and Librosa. Okay, what happens here is you specify a path, any of the files, you specify a path, and then you load the path with Librosa, and you do the same thing with SciPy. Okay, for SciPy, you use wave.read. Okay, so it gives you the same thing, in the opposite way, because here the sample rate comes first and then the audio. Here audio comes first and then the sample rate. Okay, so you do that and then you print the sample rate. Okay, and again you use the curly braces, and the variable here will be your sample rate. Okay, so you print that. Now you see the original sample rate is 44.1 kilohertz, but Liberosa gives you 22.05 kilohertz. Why is that? It's because SciPy is not specifically for audio files. Okay, it is not built um, to extract features from audio files. It has various functions. Okay, Liberosa, on the other hand, it is specifically made for audio files. So what Liberosa does, whenever it is given an audio, it will resample it. Okay, and you should know that if you have read the resources, that Liberosa resamples things and it has a lot of benefits, especially when you're trying to extract features from it. Okay, so that is why Liberosa is always a better library when you're working with audio data, since it is specifically made for it. So this is just to show you the difference. Again, here it's the same thing. You get the minimum and maximum range in these audio values. Okay, the data, whatever the data is for that file, you get the minimum maximum value. Again, SciPy will keep the original values, however large they might be. What Liberosa does, it converts them to it converts them between -1 to 1. Okay, so that is what it does. Here we have written 0 to 0.2 f. F refers to floating point number. Okay, since it is between -1 to 1, you will all obviously have decimal points there. So this is a decimal point, represents floating numbers. And what you need to do is whatever number is here, you slice it. Okay, you start from the starting, you take it from 0, and then you slice it till 0.2. Okay, 0.2 means ki, you only need 2 digits after the decimal point. You don't need more than that. Okay, so that is what this does. And you can see the difference. All right. Okay, again, this is just to show the difference. If you print the SciPy audio, you will see that you get orange and blue, 2 things here. But if you do the same thing with Liberosa, you will only have 1 because it converts any audio to mono. Again, to make calculations and feature extraction easier. It's just the same. Okay. And now you print the MFCC like you know how to do since you have done the assignment. You print the MFCC.shape. And you here what you do is you print a spectrogram of the MFCC that you have extracted. Okay. Right, and these plt.save figures, what these do is they save your data here. Okay, this PNG values. This is mfccs.png, right? So it saves it here and you can just double click it and it will, you can just see it here. Okay, it will get saved. You can download it from here only. And this image will get saved. Okay, now to the important part, the building of our model, right? This is exactly what we have done before in the last session. You create a function called extract features. You first of all, you load that file from the path. You collect the audio and the sample rate. You extract your MFCC by giving these audio and sample rate there. You can play around with the MFCC. Okay, that is your wish. You can play around with it. And then you transpose that matrix and you calculate the mean of it. And that gives you the MFCC scale. Okay, this we have already covered, so I'm not going to do it again. Here also, it's the same thing. You create a list called features, a list called labels, and from your CSV file, you take the file name, you take the raw of classes, which class does it belong to, so that you add to label, and in features, you add this MFCC scaled. Okay, so you extract the MFCC for that particular file, and that goes into features for that particular file. And then you have the label, which is class column of this book1.csv. Okay, so you add that to the label. And okay, if you print features, this will take a little time. Since it has all the MFCC values, it will look exactly as any of your MFCC value extracted looks like. Okay, like this. This is what it will look like, except it will have a lot of values there, because this we are doing it for all of the, there are about 870 870 different files here. Okay, so it is going to scale them, and these are the values you'll get. Okay, so there are, I think, 13 values each. So what will happen is, if you print the first, the shape 0 for that particular thing, which means you take the first array in your features and then you print the shape, but you print the first part of the shape. Okay, not both of them. I should have run it in another code block, but okay. Okay, so there are 13 values each. Okay. Okay, now what you do is, you have the arrays. Now you want to convert it into a data frame. Okay, so like you want to have columns and you want to have rows. So in every column, you create 2 columns. Okay, these are the only 2 things that is needed for our purpose. We create a column called features and another column called labels. In labels, we directly give the value of labels and it will happen. And in features, we give the value of the features. So every row has 13 items each. Okay, so we do that, and this creates a pandas data frame, which will make our work easier. And then if you print it, it's going to look like this. Okay, there are 13 values in each row that are MFCC scaled, and then you have the label for it. Okay, all right, now what you do is, you need to encode this. Okay, you need to use a label encoder and you need to encode this, like I have already told you how to do. So what you do is you convert this, since this is into a data frame now, right? So what you do is you create a NumPy array. Okay, so here you take features, you convert them into a list, and then you convert that list into a NumPy array and you store it into a variable called X. You do the same thing with labels. Now you get your label encoder, you do fit transform, and then you do this thing called to categorical. Okay, now what this does is, I'll show you. Okay, if you print this, okay, that is what it looks like. If you print its shape, okay, so this is what it does. I'll also print it for you. Okay, so what this does is, it has 873 rows, all right, and it has 10 columns only. So what this is it matches the values. Okay, so for example, if the 10 columns represent 10 labels, correct? So if, say, this row matches street music, for example, so what if your last column represents street music, so every other column will be 0, but the value where this is true, where this particular row represents, that will be shown with a 1. Okay, that is what to categorical does. It is one hot encoding I told you guys there is two types of encoding. First, you do this where you convert it into numbers. Okay. And then there is one hot encoding. It converts the values into encoded binary vectors. Okay. So this is what happens. Binary is either 0 or 1. So wherever it is true, whichever column it resembles, that will be 1. The rest of them will be 0. Okay, so that is what it does. And this is important when you are working with neural networks. Okay, it gives the model to work something with. It understands this language. Okay. Now you print the original labels and then coded labels. So you know that if you predict some value and say if it is 8, so you know that it represents siren. Okay. Okay, now you from sklearn, you split the data now. Okay. Now for the training data, what you are going to take is this X value, the features that were converted into a NumPy array, and then you are going to take this. Okay, this is what you're going to train your model with. Okay. So you take both of them, you split this, 20% of it will be used for testing the data, 80% will be used to train that data. And you specify a random state again, like we have already done. So you always get the same splitting. If you don't specify it, you'll always get different splitting, which is also fine. So you do that. Why not shape? We have done this. Okay, now this is important. Okay, so number of labels is y dot shape 1 because this represents the number of columns, which is equal to the number of labels, right? So we do that. And okay, filter size is not needed here. Now we define a build model graph. You define a function and we put its shape as 40 comma like nothing, 1, that is 1. So you can just experiment with this as well. Okay, so the first thing is that our model is a sequential model. What sequential means is that it will only have one input and it will only give out one output. Okay, so this is pretty much the simplest one you are ever going to find in neural networks. You only have one input and you only get one output. All right. So you will input one audio file and you will get a particular label for it as your output. So that is what the sequential model is. Now to the model, you are going to add layers. Okay, since it is a neural network, it is going to have different layers. So what you do is the first layer you add here is the dense layer. Okay, dense layer is a fully connected layer, which means that if there are say 5 neurons here, and in the next one, there are also 5 neurons. So this layer would be connected to all of them. Okay, every neuron will be connected to all of them in the previous layer. None of them would be missing. Okay, so you use all the input data you have. And here you are dividing it into 256 neurons, say. Okay. And then you add an activation function, which I have given you the resources. You must have studied about it. So you add an activation layer, the ReLU one. Then you add a dropout layer. Okay, what dropout layer is important for is what it does is, for example, you have 100 neurons here, 100 neurons in your next layer. So now after the second layer, what you do is maybe you use a dropout. Okay, so what this dropout 0.5 will do, it will set 50% of these 100 neurons to 0. Okay, so the values in those neurons would not matter now. Okay, so in this case, we have 128. So 128 neurons, values for them would be converted to 0. Now, this is important because it prevents overfitting. Okay, if you train it on every single neuron, even the slightest of change would give you incorrect results. Okay, see, I already have this. This is overfitting. This is the model we want. This is overfitting. So if you have, say, okay, see where my cursor is. If you have a data point there, it will classify it as a cross. Okay, which should not be the case because that is where all the circles are. But because of overfitting, it is giving you the incorrect results. This is where you will have the most accurate results. Okay, the highest accuracy will be in this middle graph. So what the dropout layer does is it prevents that from happening. Okay, again, you repeat the same thing because you need more layers in your neural network. So you repeat it. And then finally, what you do is you add a dense layer. And now the dense layer, the number of neurons here are 10. Okay, so now you had 256, 256, and now you have 10. Okay, now this is important because now the next layer you are adding is the activation one, and that is softmax. What softmax does, again, you should know this already, but what softmax does is it will convert the it will specify a particular probability. Okay, you have these 10 neurons, it will assign a probability value to all of them. Okay, and then you'll get your output. That is how our model is going to work. Okay, now whichever neuron has the highest probability, that is the one that will get activated, and the rest will not be activated. So that will have the this binary number 1. Okay, out of the 10, only one with the highest probability is going to have this, and the rest will have 0. Okay, so that is how our model will classify different categories. Now we are going to compile all of this finally. So we need to have a loss function, right? Because that is how the model works. It uses backpropagation, and it tries to minimize the loss function. For classification problems, categorical cross entropy is one of the best loss functions to use, so we use that. And then there is something called metrics. Okay, when you do backpropagation, there is a metric on how you evaluate if your model is good enough or not. So here we are using the accuracy metric. Okay, that is mostly what is used. And then you get an optimizer. Again, Adam optimizer is again used for back propagation. It is used to when you want to specify different weights. Okay, if you have watched the neural network videos, that is how neural networks work. So Adam optimizer is one of the optimizers that is used. So you return the model, and since this was a function in the model variable, you call your model. Okay, so you call this function, it will go here and it will create a model for you. So we do just that. Okay, this is just printing the number of labels. Okay, and you don't need to worry about the pre-training accuracy. It's not important at all. Okay, now what you do is you have the model. Now you need to train it. Okay, so what you do is you set a particular number of epochs. Epochs means one epoch refers to your model going through all your data points one time. Okay, so here we have 100 runs of that particular model. Okay, so 100 times it will do back propagation and it will do everything, which will give you a good model. Okay, and then there is the batch size, which means that out of whatever number of items you have in your particular data, out of those, during one iteration, during one epoch, 32 will be used. Okay, you can increase or decrease that number based on whatever your requirements are. But here we have taken only 32. Now you fit it into the model. Okay, so you do that. And for the validation data, you have your testing data. So, okay, so you run that. Okay, you see every epoch is running, and this accuracy value. Okay, see this loss function. This is the value for the loss function. This is the accuracy value. Again, loss function and accuracy value. The first two are for your training data. The next two are for your testing data. You will see that the accuracy in both keeps on increasing, and the value of loss function keeps on decreasing as we go. Okay. Now we are done with all the 100 iterations. This was quick because there's not a lot of data, even if it's like 870 plus data, but for neural networks, it's not that big data. Okay, so that happens. And now you evaluate your model. Okay. And you print the score 1 because the 0 will be the loss value. Okay. 0 is the loss value, 1 is the accuracy value. So for the training as well as testing data, you print the first one. So you get the accuracy. Okay, see, that's it. Okay, and in most of the cases, you will see that your training accuracy is better than your testing accuracy. Okay, and if you print the score, see, this is what you'll find. This is the value of your loss function, and this is your accuracy. Now, what we go and do is we try to predict something. Okay. Here we have taken a very random audio, whichever it is, and then we extract features from it. We created a function called extract features, right? So we extract the features, we put those values in prediction features, and then we need to reshape it. Okay, we need to, because it is an MFCC value, right? So what we need to do is we need to convert it into one row. And this -1 means that the number of columns will be decided based on however many rows and columns are there. Okay, if say that our MFCC has 5 columns and 2 rows. Okay, now you want to convert it into one row. So one you have specified already, and -1 will see itself that, okay, if there is one row, there needs to be 10 columns, right? So that is what it does. So you convert that into one row, and then you do model.predict, and you give it these features to it, and it will predict that. Okay, and now you need to predict the label. Okay, see, these are the probability values. Okay, for different all the 10 numbers you have, it gives you the probability values. Okay, how probable is this? Okay, so now you do the predict label. You use the argmax function, which gives you the maximum probability one, it returns that. So the predicted label here is 2. Okay, for 2, where it is. Okay, here it is. Okay, so 2 we have children playing. Okay. And I think I have it downloaded. Yep, this is the one. See, if you could hear it, it is actually children playing. Okay, so that is what our model did, and that is how these works. You just add on layers, and this is a simple model, so you did not have a lot of layers, but maximum time there are a lot of hidden layers, a lot of different connections, and that is how a neural network works.